If you throw a body vertically upwards with some velocity from the ground, it attains the height where its velocity becomes 0 and then returns to the point of projection. As soon as the body is thrown, it is under G acting towards the center of the earth. When the body is on its way up, it is under retardation till it attains 0 velocity and then returns to the ground due to gravitational pull. Here, as the body moves up, its kinetic energy is converted into potential energy. This is based on the law of conservation of energy, that the total energy of the system remains constant. Thus, it is obvious that if the velocity of projection is increased, the maximum height attained by the body increases. But whatever the maximum height attained by the body projected vertically upwards, you feel that the body comes back to the earth. Is it possible to project a body vertically upwards at such great speed that it does not return to the ground? Here's another way to ask the same question. Is it possible to project a body vertically upwards with a speed that allows it to escape the gravitational field of the earth? If it is possible, the speed will be the escape speed of the object. Sometimes, escape speed is also referred to as escape velocity. For the time being, assume this is possible. In this case, does the escape speed of different objects depend on their masses? Let's answer the question with the same example. Consider a position A on the surface of the earth, from where the body of mass m is projected vertically upwards with velocity u. Then, its kinetic energy at the surface of the earth is given by half mu square. Let this be equation 1. The potential energy of the earth body system at the earth's surface is denoted by PEA is equal to minus GMEM divided by RE. Let this be equation 2. In this equation, ME is the mass of the earth and RE is the radius of the earth. Thus, the total energy of the body on the surface of the earth when it is projected vertically upwards is the sum of its kinetic and potential energies, and is denoted by the expression TEA is equal to half mu square minus GMEM divided by RE. Let this be equation 3. Now, assume the body moves continuously in the upward direction with a continuous change in its velocity. At position B, the height gained by the body is h, and its velocity at this position is v. Then the kinetic energy of the body at the height gained is expressed as half mv square. Let this be equation 4. The potential energy of the earth body system when the body is at height h is denoted by the equation PEB is equal to minus GMEM divided by RE plus h. Let this be equation 5. Thus, the total energy of the body at position B is expressed as the sum of equations 4 and 5. Let this expression be equation 6. According to the law of conservation of energy, the total energy of the Earth body system at position B is equal to the total energy at position A, denoted by equation 7. On submitting the corresponding terms for the respective energies in equation 7 and on further simplification, you get the equation for kinetic energy of the body at the given height, as expressed in equation 8. The height gained by the body projected vertically upwards is maximum when its velocity v becomes 0. This is possible when the sum of all the terms on the right side of equation 8 is equal to 0. In case velocity v always has a positive value, then the body continues to move vertically upwards, thus increasing the value of h to infinity, which eventually happens when the body escapes the gravitational field of the Earth. This is possible when the combination of the terms in the right side of equation 8 is greater than or equal to 0 for any value of height h. Thus, the minimum value of u can be obtained by equating the expression to 0. Also, when h becomes infinity, the expression that includes h in equation 8 becomes 0. Rearranging the terms in the equation and simplifying, you get the value of u as given by the equation u is equal to square root of 2 gme divided by re. Let this be equation 9. If this was the minimum value of velocity of projection of a body vertically upwards, then the body would escape the Earth's gravitational field. Thus, equation 9 represents the expression for the escape speed of a body on the surface of the Earth. It is clear from the expression that the value of the escape speed of a body on a given planet does not depend on the mass of the body. It depends on the mass of the planet and the radius of the planet. If the body is projected from a height h from the surface of the Earth, then the escape speed from that height is obtained by replacing the denominator of equation 9 with re plus h as shown in equation 10. Using the relation of acceleration due to gravity on the surface of the Earth and the mass, radius of the Earth and universal gravitational constant, and simplifying, you get equation 11. Satellites are celestial objects that revolve around planets. As planets themselves revolve around the Sun, they too are considered satellites. Thus, Kepler's laws of motion are applicable to satellites too. The Earth's natural satellite is the Moon. The orbit of the Moon is nearly circular. Hence, the Moon is under the action of a centripetal force. This centripetal force is provided by the gravitational force between the Earth and the Moon. Now, consider the height of the Moon from the surface of the Earth as h and re as the radius of the Earth. then the effective radius of the moon's orbit is Re plus h. The centripetal force on the moon is expressed as Fc is equal to mv square by Re plus h, where m is the mass of the moon and v is the speed of the moon in its orbit. The speed of the moon in its orbit is also referred to as orbital speed. Let this expression be equation 1. The gravitational force between the moon and the earth is expressed as Fg is equal to gmem by Re plus h square, where me is the mass of the earth. Let this be equation 2. Equating the two equations and simplifying, you get the expression for the speed of the moon in its orbit as square root of gme divided by Re plus h. Let this be equation 3. Once you know the expression for the speed of moon in its orbit, you can find the kinetic energy of the moon using the expression Ke is equal to half mv square. Substituting the expression for speed from equation 3 in the expression for kinetic energy, you get the expression for kinetic energy as Ke is equal to half m gme divided by Re plus h. Let this be equation 4. Earlier, you learnt about the potential energy of a two-body system. Applying the concept of potential energy to the Earth-Moon system, you get the expression for potential energy as Pe is equal to minus gmem divided by Re plus h. Let this be equation 5. Now the total energy of the moon in its orbit is determined by the sum of its kinetic energy and potential energy. Thus, the total energy of the moon or any given satellite revolving in its orbit around the Earth at a given height is expressed as minus of gmem divided by 2 times Re plus h. The total energy of an orbiting satellite is found to be negative. Let this be equation 6. Now, let's see what happens if the orbit of a given satellite is close to the surface of the Earth. In this case, the height h of the satellite becomes negligible when compared to the radius of the Earth. Thus, h in equation 6 can be neglected, and you get the expression for total energy of an orbiting satellite as Te is equal to minus gmem divided by 2Re. Let this be equation 7. The speed of the satellite in its orbit is obtained by substituting 0 for h in equation 3. This gives the speed of the satellite in its orbit as v equal to square root of gme by Re. Let this be equation 8. Using the relation between acceleration due to gravity on the surface of the Earth and the universal gravitational constant, the orbital speed of the satellite can be expressed as v equals square root of GRE. Let this be equation 9. The speed of the orbiting satellite can also be obtained using the relation between the time taken by the orbiting satellite in its orbit, t, also known as the period of the satellite, and the length of the orbit. As the orbit is circular, the length of the orbit is the circumference of the circle, 2 pi re. Thus, the speed of the satellite in its orbit is given by the expression v is equal to 2 pi re divided by t. On rearranging the expression, you get the time period as t is equal to 2 pi re divided by v. Substituting the expression for v from equation 8. In this expression, and simplifying, you get the square of the time period proportional to the cube of the radius of the orbit. This expression shows that it is in compliance with Kepler's third law. In today's world, communication plays an important role. Satellites are used for effective communication. Apart from communication, satellites are used for various purposes ranging from analysis of weather conditions in a region, live transmission of cricket matches through television, exploration of minerals from the Earth, and for geographical purposes. Satellites used for various purposes are artificial satellites. In a broader sense, there are two categories of artificial satellites, namely geosynchronous and sun-synchronous satellites. First, you will learn about geosynchronous satellites. Earlier, you learned that the speed of an Earth satellite in its orbit is denoted by the expression v is equal to 2 pi into re plus h divided by t, where re is the radius of the Earth. H is the height of the satellite from the Earth's surface, and t is the time taken by the satellite to complete one revolution around the Earth, which is referred to as its time period. Let this be equation 1. The speed of a satellite in its orbit can also be obtained using the relation v is equal to the square root of gme divided by re plus h, where me is the mass of the Earth and g is the universal gravitational constant. Let this be equation 2. Equating expressions 1 and 2 and simplifying, you get the expression for h, as shown in equation 3. Knowing the data for the mass of the Earth, its radius and universal gravitational constant, you can estimate the height of the satellite for which the period of revolution is 24 hours. This is done by substituting the corresponding values in equation 3 and simplifying as shown. Thus, a satellite whose height from the surface of the Earth is about 35,850 kilometers has a period of revolution equal to that of the period of rotation of the Earth. If the orbit of the satellite is in the equatorial plane of the Earth, then the satellite appears to be stationary relative to a position on the surface of the Earth. Such satellites are called geostationary satellites or geosynchronous satellites, as their motion in their orbit is synchronized with the rotation of the Earth. Generally, this type of satellite is used for telecommunications and mass communications. The International Satellite System, generally referred to as INSAT, is a series of geostationary satellites set up by Indian Space Research Organisation (ISRO) to cater the meteorological, telecommunications and broadcasting needs of the country. Now, you will learn about the second type of artificial satellite, a sun-synchronous satellite, also referred to as a polar satellite. The altitude of a polar satellite is lower than that of a geostationary satellite. That is, in the range of 700 to 1,700 kilometers. Accordingly, the time period of such a satellite is of the order of a few hours. The orbit of these satellites is such that the satellite moves in a plane that is near normal to the equatorial plane, moving closely to the poles of the Earth for every revolution, while the Earth rotates in west to east direction. Why are these planets called sun-synchronous? As you know, the local time at a given place on the Earth depends on the longitude of the place. With the rotation of the Earth, the local time at a given place changes with the relative position of the Sun. The orbit of a sun-synchronous satellite is designed in such a way that the angle between the plane of the orbit and the line joining the Earth and the Sun are fixed. This maintains consistency in the lightning conditions of a given place. When a satellite revolves around the Earth, successive north-south passes are displaced the same distance as the Earth rotates during one orbital period of the satellite. As a result, the satellite covers the given place at the same local sun time daily. Thus, the motion of the satellite is synchronized with the local sun time at the given place. Hence, these types of satellites are called sun-synchronous satellites. As they cover the polar regions for every revolution, these satellites are referred to as polar satellites. As the altitude of a polar satellite is less, a camera fixed to the satellite can scan only a small strip of the Earth in one revolution. For the next revolution, as the Earth rotates on its axis, the adjacent strip of the Earth is scanned. Thus, in a single day, the whole of the Earth is scanned in a series of strips. Indian Remote Sensing Satellites, generally referred to as IRS, which are used for remote sensing applications, environmental studies, weather analysis, forecasting, and similar applications, are examples of polar satellites. Artificial satellites are generally unmanned. At times, cosmonauts are sent along with satellites into space to conduct certain studies. In space, they feel zero gravity or weightlessness. The weight of a body is the force experienced by the body due to the gravitational pull of the Earth. A spring balance that measures the weight of a body works on the principle of extension of the spring. Under the action of the weight of the body attached to the balance, which is fixed to a rigid support. While measuring the weight of the body attached to the balance, the body is pulled downwards due to the Earth's gravity. It, in turn, exerts the same force on the spring downwards, causing its extension. This is indicated in the reading of the balance. If the balance is not suspended to the rigid support and is allowed to fall freely, then both the body and the spring balance fall down, with acceleration due to gravity. In this case, the force exerted on the body by the balance is zero. Hence, the stretching of the spring is zero. Thus, the spring balance reads zero weight of the body. This situation is the weightlessness of the body. Thus, we can say that a body experiences zero gravity or weightlessness in a free fall. In the case of a satellite orbiting the Earth, it is similar to any other freely falling body. But it has very high velocity in the tangential direction of its orbit, due to which it misses the Earth as it falls. Thus, every part of the satellite is in a state of free fall, and it is subjected to acceleration due to gravity in that position. Hence, cosmonauts in manned satellites experience weightlessness.